Colombia is really special, and one thing about Colombia that's special is that everybody is so close together. I think it's a big advantage. We collaborate much more because we see each other much more, because we are close together, and I think the Northwest Corner building will bring it all together.
Neuroscience right now is in a very exciting time because many of us have the feeling that the big breakthrough is just about to occur. There's been a slew of new techniques coming into neuroscience from other fields, particularly from the physical sciences, from physics, from chemistry, from engineering. And these techniques have revolutionized the type of data that we have on brain circuits.
To really compete effectively and to really work at the cutting edge, you need to have access to tremendous resources in terms of instrumentation. Having that instrumentation all housed in a single building where, in essence, each instrument is run by an expert in that field residing on their own floor is just a fantastic opportunity for us to push our research forward.
I'm trying to develop a new field of science, which is mechanical biochemistry. So in my laboratory, I have people doing standard protein biochemistry, engineering proteins for our experiments. I have physicists doing theory. I have people with inclination to do analog electronics and integrated circuit development. So we end up building our own instruments and analyzing our own data with our own tools and developing our own theory.
So in my lab, we're interested in combining biological and chemical methods. So the questions we have are in biology, like how does cell death operate, and how does cell death operate in tumor cells and in neuronal cells, leading to these disease processes. It turns out that all of the drugs that have ever been created interact with only 2% of the proteins in our cells. And the vast majority of the remaining proteins are considered undruggable, particularly in diseases like cancer and neurodegeneration where cell death goes awry. We'd like to understand and ultimately try to correct those problems.
In the cell, we have to figure out how to do chemistry, how to manipulate the structure and function of molecules in this very complex environment, a very crowded environment, jam-packed with molecules with all sorts of functions constantly occurring. And so our strategy is, rather than trying to add something into the cell that's completely artificial, we're trying to co-opt the cell's own machineries for doing chemistry and just expand and redirect the chemistry that they can do.
Our angle is to try to attack it the same way that engineers attack electronic circuits. They apply a rigorous process of research, which is called reverse engineering. So this is exactly what we're trying to do to the cerebral cortex. Take apart its circuits, write it down in a piece of paper one day, the connectivity pattern, and if we're clever enough looking at it, we can figure out what we're dealing with.
People are putting more and more electronic circuits in smaller and smaller areas. So we actually make things and then measure their properties, and then we work with theorists to help understand what we measure. Because once you shrink down sizes of integrated circuits, which are things in your computer, you need to know how things work at this scale.
It's a new field of science, which is made possible by new tools and a new sort of concepts that have been developed over the past 20 years. And I have, together with colleagues over the past 15 years, developed a number of modifications of the atomic force microscope that allow me to study the effect of force on single individual proteins for the first time.
The long-term practical outcome of our research would be developing new tools for engineering cells that you could use therapeutically.
I'm optimistic that maybe eventually these approaches will be successful at creating drugs, but it's going to be a difficult problem that will need a lot of work.
In the future, researchers will not be really interested too much in what disciplines they are belong to, but in what problem they are trying to solve. And this is the type of spirit that we want to instill into our students and become fearless scientists that will actually help move science forward into new territories.